Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. My topic for this morning will be the computation of line current if the load is unbalanced and it is three-phase. Okay, let's proceed. Let's proceed. We are given an unbalanced delta load. Okay. The given specifications that we are given C1, C2, and C3, and we are given the magnitude of the input voltages. It's 220, 220, and 220. The problem is just asking what will be the magnitude of line current IA, IB, and IC if the phase sequence is ABC. Phase sequence is ABC. Okay, let's try to bring out the solution of this one. If we try to bring out the solution of this one here, okay, I'll try to zoom out. Yeah, I saw it. If the phase sequence is ABC, under the study of AC circuit, if the phase sequence is ABC, the designation of the input voltages will be BAB will be 220 angle 0, BBC will be 220 angle 120, and B sub C will be angle or the magnitude is 220 angle minus 128. The input voltages is balanced, but since the load is unbalanced, of course, the three line currents coming in should be unbalanced. Okay? To bring out or to compute for the current in its line, we consider the three terminals here. Okay? For IA, the equation will be this one here. That is the difference of IAB minus I sub CA. For IB, it will be the difference between IBC and I sub AB. Okay? So the requirement here is to compute for this line current here, we must have to compute this current and this current if we try to compute for IA. If we try to compute for IB, we must have to know this current here and this current. And to compute for I sub C, we must have to compute for this current and this current. And to compute the individual phase current, voltage is equal to IC, right? So if we know the voltage, we know the impedance, we could compute for the current. But to compute for the current, we must have to change the form of the impedances because the impedances are actually in terms of rectangular. So we must have to convert this 3 plus G4, 5 minus G2 to 6 plus G0 into polar form because we needed the magnitude. And for Z1, this is the magnitude, or this is the value of Z1 in terms of what do you call this polar form. The magnitude is 5, 53.13 degrees. To compute for this, it's just the application of trigonometry. It seems we are given a vertical height 4, horizontal distance 3, and we are computing for the angle between 4 and 3. So we take tangent, we take the ratio 4 over 3, divide 4 over 3, then we compute for the arctangent of that, what will come out for the angle will be 53.30 degrees. The real part is just the magnitude will be the real part divided by the cosine of this one. Second solution, take the imaginary part divided by the sine of this one. It will still be 5. Same true with C2. Okay. It will come out 5.38, negative 21.8. This negative because this is minus G2 capacity. Right? And for C3, it's an easy one, 6 plus G0. It's a pure resistance. So 6 plus G0 is just the magnitude is 6, the angle is 0. Okay, so by using the equation voltage equal to IC, we could compute for the individual phase current. Uh, IAB is actually equal to IC1. So I just designate this one as IC1 now will be BAB over C1. Okay? Uh, we are performing complex operation here. So this will be 220 angle 0 over 5 angle 53.30 degrees. We use these voltages here, including the angle, because we are performing complex operation. Right? So what comes out for I sub C1 in terms of rectangular, because later on we are subtracting two currents. So I changed already the polar equivalent to rectangular, that is 26.4 minus J 35.2. For I sub C2, it's the same. Same, same formula, but the voltage will be, we will be taking B sub BC over C2. 220 angles 120 divided by 5.38 negative 21.8. This will become 141.8. So in terms of rectangular, this should be the current. Right? For current C3, should be the voltage between C and A. So this is B sub CA over C3. 220 angle minus 120 over angle or over 6 angle 0. 36.67 angle minus 120. Minus 120 minus 0 is still minus 120. Negative 120 on the third quadrant. I sub C3. This will be the current I sub C3. It's in the third quadrant. Real part negative, imaginary part negative, so this will be the magnitude 36.67. So in terms of rectangular, this will be the rectangular equivalent. Right? So if we now try to compute for IA, considering this junction, IA, current entering is also I sub CA plus I sub CA. The current coming out from here is actually IAB. So we are looking for this one here. Right? So I sub A now, line current IA will be the difference IAB minus I sub CE. So since our currents are already in rectangular, it's just a matter of subtraction. This will be I sub C1 or I sub AB. This is I sub C3. Real, imaginary. Okay, what comes out? 26.4 plus 18.33. This is minus inside, so this 18.33 should be added to this 26.4. So what comes out is 44.73 minus J 3.45. We do not know yet the magnitude because this is in rectangular form. So we must have to convert this one to polar. And if we try to convert that to polar, the magnitude will be 44.86 amperes. So this one here is 44.86 amperes. That's the total magnitude. For I sub B, consider this junction here. Current entering here is I sub B. Current entering is IAB. So this will be IB plus IAB. The current coming out is I sub CA. This is I sub CA. Where is it? I sub B. Oh, I sub BC. We are computing for I sub B. So I sub B will be the difference I sub BC minus I sub AB. I sub BC is I current across I sub C2 minus I sub C1. They are now in rectangular, so if we try to perform the operation, the real part will be negative 58.83, the imaginary part will be 60.48, and the location of the current I sub C3 is actually 134.06 degrees. I sub C3, no, I sub B, hold on. Oh, this is I sub B. The real part is negative, the imaginary part is positive, so negative and positive, this will be the magnitude of I sub B. And with respect to the 0 degree, we always put the angle of the currents with reference to the 0. So that will be 134.06 degrees. So this is 134.06 degrees. Okay. That's it, guys. For I sub C, I didn't show you any more the solution because I sub C will be the difference I sub CA minus I sub BC. I didn't show you any more the final magnitude, but you just take the difference of I sub CA minus I sub BC. Anyway, they are now all in rectangular, then convert that to polar. Okay? So I sub B, I will write, this is I sub B, this is 84.16 amperes. This is the biggest current. For I sub C, I didn't show you anymore the, what you call this, the computation, but the procedure on how to compute, consider this junction, it should be the difference I sub CA minus I sub BC. Okay, I sub CA minus I sub BC. Just substitute the value I sub BC, I sub CA, I sub C is actually I sub C3, and I sub BC is actually I sub C2. We now know the value of this was in rectangular. We perform the rectangular addition, then change that to polar. What will come out? We could compute for I sub CA. Okay, that's it, guys. That's the way on how to compute for the individual line currents if the load voltage or the input voltage are balanced, but unluckily the load on its phase for a delta connected load is unbalanced. So this is 44.86, this is 84.16. This one we do not know yet the value, just continue the operation there. So this is actually a topic on the so-called computation of line currents for unbalanced three-phase load. The input voltages is balanced, but the loads that are connected in delta connection is actually unbalanced. So supposed to be the current in its line will be different. And actually that's the worst case scenario in real life. Because when we try to connect circuits, we are not sure if all the loads are balanced because it's hard to balance the load in its phase for a three-phase delta load. Okay, that's it, guys. So for those of you who would like to subscribe to my channel is at youtube.com/Prof. David J. De Los Reyes. If you want to share it, please click share. Good morning from Los Angeles. This is Professor David J. De Los Reyes.